Okay, here's an illustration of the construction. And these diagrams are copied from Sipser's book. So the idea is based on what's known as the tableau of the Turing machine M on a given input X. So the tableau over here on the left is a table, a T by T table. And each row of the table contains the configuration of the Turing machine at the given time. So on the top row is the initial configuration of the Turing machine. Then the next row would be the configuration after one time step, and so on. So the configuration contains the contents of the tape together with the location of the tape head and the current state. So initially, the first n cells will contain the input X, followed by blank symbols out to out to column T of n. And the first cell will contain also the initial state Q0, indicating that the tape head is at the leftmost location in its initial state. Okay, and so for example, if the first step of the Turing machine were to overwrite this with a 1 and then move the tape head to the right, then the next configuration would have 1, 0, 1, 0, and in the second cell we'd additionally have whatever the state is at that point. Good, and we can assume without loss of generality that the Turing machine always halts with the head in the leftmost position. So therefore, to determine whether or not the machine accepts, it suffices to look in the contents of the leftmost cell, the bottom left cell. Now, so the idea of the circuits which simulate this tableau is as follows. So each cell in the tableau, we can represent the information in that cell using a constant number of bits. Okay, so we'll have a constant number of gates which are computing the like a 0, 1 representation of the tape of the information in that cell. And so what is the information in that cell? We have the symbol of the tape alphabet. We have, a bit indicating whether or not the tape head is at that location, and we have the current state of the Turing machine in the case that the head is at that location. So the observation is that, well, we only need a constant number of bits to represent that information. In particular, log of the size of the tape alphabet plus log of the number of states is sufficient. And now, if we look at any cell in the tableau, so this cell here, for instance, we can observe that the contents of that cell are completely determined by the contents of the 3 cells above it, right? So if the Turing machine head at the previous time step is not in one of these 3 locations, then we know that we just copy the entry above, right? And otherwise, it's just a local computation. And so in our circuit, the circuit will be divided into blocks corresponding to the cells of the tableau. Maybe at the top you have the gates, which are representing the actual data there, and then to compute that data from the cells above, you can do this with constant size Boolean circuits. And here I note that this circuit illustration here, the wires are being drawn like pointing downwards. In the rest of this lecture, I'm drawing my circuits the other way with wires pointing up. But anyway, you get the idea. So this is just a sketch of how this simulation works, right? And we can see that the size of the resulting circuits is t of n squared. I wanted to mention that a more efficient simulation is in fact known. So there exists circuits of size t log t, which simulate a time t Turing machine. So just to outline how that goes. So the first step is to convert any Turing machine M into what's known as an oblivious Turing machine M prime with running time t prime equals t log t. And oblivious means that the sequence of left to right head movements of M prime is a function of the input length alone. So on any two strings of the same length, if you're only looking at the sequence of head movements of M prime, they will be the same. Okay, good. So let's take that step for granted. That's a theorem of Fisher and Pippinger. Then the second step, which I leave as an exercise, is to convert M prime, with the oblivious Turing machine M prime, to a sequence of equivalent circuits of size order T prime. Okay, so there's a linear size simulation of oblivious Turing machines. Okay, good. So we've now defined the class P/poly, and we've proved that it contains the class P. So next, I'm going to describe alternative characterizations of both of these complexity classes. So both P and P/poly can be characterized both in terms of Turing machines and in terms of circuits. So we'll define this one first. So okay, so this is the notion of a Turing machine with advice. So let alpha be a function from natural numbers to strings. So we can also think of alpha as just a sequence of strings. So a Turing machine with advice alpha is defined as a two-tape Turing machine with one standard input work tape and a second tape, which is initialized to the string alpha n on inputs of length n. Okay, so this is a Turing machine with advice. And so the theorem is that a language is in P/poly if and only if there exists an advice function such that L is computed on all inputs by a Turing machine with advice alpha. And just a remark here that without loss of generality, we can assume that alpha has polynomial length. Alpha n has length poly n, simply because a polytime Turing machine can only access poly n bits of the advice string alpha. Okay, and right, so I'll leave the proof of this as an exercise. And did want to mention that this is the standard definition, in fact, of P/poly. So this theorem is really showing that this definition is equivalent to the one we gave in terms of poly-size circuits. Good. So we can also characterize the class P, so polytime languages, in terms of circuits. And this is via the notion of uniform circuits. So here's the definition. We say that a sequence of polynomial size circuits is uniform if there exists a polynomial time Turing machine G, so a circuit generating Turing machine, such that on input 1 to the n, so a string of ones of length n, G outputs a description of the nth circuit. Okay, so description as some poly length string under any reasonable encoding. Okay, so this is the notion of uniform. So earlier we were saying, in the definition of P/poly, this sequence could be any, sequence of circuits. To say that it's uniform means that there's a polytime process which is producing these circuits. Okay, and then so the theorem is that a language is in P if and only if it's recognized by a uniform sequence of poly-size circuits. So the proof of this, so one direction we essentially already saw the proof of. If you just consider this simulation of a time t Turing machine by circuits of size t squared, well, you see that is in fact a uniform sequence of circuits. That process we described, you can regard that as a polytime algorithm. In the opposite direction, suppose we have a uniform sequence of poly-size circuits generated by some Turing machine G, then we get a polytime language by, on input X, we first run the machine G on 1 to the n, where n is the length of X. This produces some circuit Cn, and then we simulate that circuit, which can be done also by a polytime Turing machine. Each of these steps is polynomial time, so this produces a polytime algorithm for our language. And just to mention that there's even weaker notions of uniformity, which lead to the equivalent definition of p/poly, or sorry, of p. So you can even take G to be a log space Turing machine. So this is known as log space uniformity. Okay, so to recap, we've now seen definitions of both P and P/poly in terms of Turing machines and circuits. And yeah, so we've seen that P is a subclass of P/poly. So the question arises, where does NP fit into this picture? Well, of course, NP contains P. On the other hand, it does not contain P/poly. So as mentioned earlier, P/poly even contains undecidable languages, whereas certainly every language in P or NP is decidable. That's one way of showing it. You can also argue that P and NP are countable languages. They're countably infinite, as are the class of decidable languages, whereas the class P/poly is uncountable. Okay. What about, so we know that P/poly is not contained in NP, but what about the converse? So is NP a subclass of P/poly? Well, we can observe that if P equals NP, then indeed NP is a subclass of P/poly. And the contrapositive is that if NP is not contained in P/poly, so in other words, if NP languages, do not have poly-sci circuits, then P is different from NP. Okay, so this leads to the observation that circuit lower bounds are a concrete combinatorial way of potentially separating P from NP. So we saw that almost all Boolean functions require exponential size circuits. But proving lower bounds for any specific Boolean function would have great consequences. And just to restate what we just observed, if any language in NP, for instance, satisfiability, in fact, without loss of generality, you could consider any NP complete problem. So if any language in NP has super polynomial circuit size, okay, so larger than omega n to the c for every constant c, well, that shows that NP is not contained in P/poly, and therefore P not equal to NP. Okay, so this is one of the reasons to study circuit complexity is that it provides a combinatorial version of this P versus NP problem, and we can hope to study these important questions from that perspective. And so this is as I said, the holy grail of circuit complexity, to prove a super polynomial lower bound on the circuit size of any explicit sequence of Boolean functions. So yeah, unfortunately, proving lower bounds is hard. And this is illustrated, I think, by considering the sequence of world records of the strongest known lower bounds for explicit Boolean functions, here measured in terms of the number of and or gates in Boolean circuits. And as you can see, progress on lower bounds has been very, very slow. And currently, the strongest lower bound known is just shy of 5n. Okay, so we have merely linear lower bounds, whereas we need a super polynomial lower bound to resolve big open questions. People have also considered circuits in the so-called full binary basis. So if we allow all binary Boolean functions as gates in a circuit, This is a more powerful model than just Boolean circuits, so the lower bounds are even weaker. And as you can see, yeah, progress is similarly slow. There was recently, in fact, a breakthrough improving longstanding 3n lower bound to 3 plus 1 over 86. But I think this well illustrates the challenge of proving circuit lower bounds. So next, I wanted to say something about the technique that's used to prove these lower bounds. This is known as the gate elimination method. Okay, and the idea is pretty simple. So we want to prove a lower bound on circuit size. So let's say a linear lower bound of the form c times n for some constant c. So suppose we could do the following. We could repeatedly pick some variable xi and assign it to either 0 or 1 in a way that eliminates at least c gates from our circuit each time we do this. So let me illustrate what I mean. So here, consider the variable x2. And suppose we substitute 1 for x2. And let's see how this simplifies the circuit. So consider this AND gate. We have a 1 feeding into an AND gate, but this means that the gate only depends, therefore, on its other argument. So this lets us eliminate this wire. And now we have this OR gate. So we have a 1 feeding into an OR gate. So that means that the OR gate will produce the value 1, no matter what its other argument is. So we can eliminate that gate and sort of propagate this 1. And now we have a 1 feeding into 2 AND gates. So as we saw, we can eliminate those wires. And we can perform additional simplifications. We have these 3 gates here, which receive only 1 wire. So this means that we can bypass those gates and just put wires directly, like this. We could even notice now we have 2 negation gates, and therefore they cancel each other. So just by some local simplification process, we've reduced our circuit to this form. And so here you can see the gates that we've eliminated. So in this case, we've eliminated 6 gates. So assuming you could do this, eliminate at least C gates, for at least a constant fraction of the time, this would give you some bound, lower bound, say Cn, if you could always do this. And I'll leave it as an exercise to show that, using this exact method, you can prove a tight lower bound of 3n minus 3 on the number of AND and OR gates in any Boolean circuit computing the parity function. So we already saw earlier that this 3n minus 3 is an upper bound, and you can prove that this is exactly tight using this simple argument. Okay, so this is the gate elimination technique. And let's recap what we've seen so far. So we've defined Boolean functions and Boolean circuits, and we proved Shannon's theorem that almost all Boolean functions require exponential circuit size. We've defined the class P/Poly, both in terms of Turing machines, circuits, and in terms of Turing machines with advice. And we've given a proof that P is contained in P/Poly via this quadratic simulation of Turing machines by circuits. And we discussed the holy grail of circuit complexity, which is to prove a super polynomial lower bound on the circuit size of explicit Boolean functions. And this would imply P not equal to NP. And we had a look at the history of lower bounds known to date, so far merely linear, and we gave a sketch of a gate elimination method which can be used to prove some of these lower bounds. So next, let's have a look at some of the other computational resources of Turing machines on the one hand and circuits on the other hand. So in the setting of Turing machines, we study time complexity, space complexity, randomness. And for Boolean circuits, we've already discussed size, we defined but haven't yet discussed depth as a resource. You could also look at width of Boolean circuits. So if we have a Boolean circuit where the gates are arranged in layers with wires going from one layer to the next, then the width would be the maximum number of gates on any layer. And we saw that time complexity on Turing machines corresponds to circuit size. So space complexity turns out to correspond in a similar way to circuit width. And analogous to definition of P/poly, there's the class log space / poly. And this turns out to be equivalent to the class of languages recognized by polynomial size log width circuits. Just to mention, in many of the classes we study in circuit complexity turn out to have equivalent characterizations, many different equivalent characterizations. In the case of log space / poly, this is also the class of languages recognized by polynomial size branching programs. So I'm not going to define branching programs, but if you've seen decision trees before, then branching programs are like a circuit version of decision trees. So randomness is an interesting resource in the setting of Turing machines, in the setting of uniform complexity theory. It turns out that in the setting of non-uniform Boolean circuits, randomness does not increase their power. So you can show that P/poly equals BPP/poly, so in the non-uniform setting. And I'll give a very quick sketch of how the proof of that result goes. So let's just show that uniform BPP, which the class that you've encountered so far, so randomized polytime algorithms, is contained in P/poly, poly-sized circuits. So you can also think of this result as saying that non-uniformity is more powerful than randomness. So here's a sketch of the proof. So consider a language L in the class BPP. So this means that there exists a randomized polytime algorithm A that decides membership in L, and it gives the correct output with probability at least 2/3 on any for any x. So now we're going to define another polytime algorithm A prime, which is simply to run the algorithm A some order n times and output the majority answer. So output the majority answer. And one can easily show using the Chernoff bound that A prime is correct with probability at least 1 minus 1 over 2 to the n. Okay, so we can take some error 1/3, and we can reduce it all the way down to exponentially small error by just repeating the randomized experiment some order n times with independent randomness each time. Okay, so this is still a polytime randomized algorithm. And now, by the magic of the probabilistic method, it follows that there exists some choice of the random seed for this algorithm A prime, such that A prime is correct on all inputs. So because the number of inputs is 2 to the n, and we've reduced the error probability down to below 1 over 2 to the n, it follows that there's some choice of the random seed for which this algorithm is correct on all inputs of length n. Great, so now it follows immediately that this L is therefore computable by a polynomial time Turing machine with this advice string alpha, right? You just simply run A prime with alpha playing the role of the randomness. And therefore, by our characterization of P/poly in terms of polytime Turing machines with advice, this shows that L is in P/poly. Okay, so this is the proof that non-uniformity is more powerful than randomness. So finally, we come to the very interesting resource of Boolean circuits, which is the depth. So recall that the depth of the circuit is the length of the longest path from an input to the output gate. And this measure corresponds to parallel time, so it corresponds to time for parallel algorithms with multiple processors. But it's also tightly connected to another complexity measure called formula size. So let me now define for you what are formulas. So formulas are simply circuits, Boolean circuits, with the structure of a tree. Okay, meaning each gate has, or each node in the formula has out degree 1. Okay, so this means that it will have the structure of a tree. Whereas in a general circuit, you can have a gate which feeds its result to multiple gates above it. And you can think of formulas as being a memoryless model of computation, in the sense that the result of each sub-computation gets used only once. So each gate only feeds its answer, to one gate above it. And, intuitively, this should mean that formulas are a weak model of computation. This correspondence between circuit depth and formula size is made concrete by the following theorem. So first, every circuit of depth d is equivalent to a formula of size at most 2 to the d. Okay, and we'll see the proof of this in a moment. And then the more interesting direction, every formula of size s is equivalent to a formula of depth order log s. Okay, and therefore, by part 1, the size will be s2 to the order log s, so s to some constant. Okay, so in other words, this is saying that with a polynomial blow up in size, we can balance a formula so that it has depth which is just logarithmic. And I'm going to illustrate the proof, give a proof by picture of both parts of this theorem. So for part 1, we're just going to convert a circuit to a formula in the obvious way. So for each gate in the circuit, if it has, takes 2 subcircuits that feed into it, we just make disjoint copies of those subcircuits, and then we repeat this process. So starting at the root, you do this, and then repeat this process inside of the red triangle and the yellow subcircuit. Okay, and you do this all the way down, and it's easy to show that the formula size that you get is at most 2 to the d. Okay, so for the other direction, we're going to start off with a formula of size s, and we're going to show how we can convert it to a formula of depth order log s. So here, consider this orange formula of size s. So the first step is we're going to split this formula. We're going to find some edge, some wire that is in this formula, where if you remove that wire, you'd split the formula into 2 subformulas, each of size, between 1/3 s and 2/3 s. So the claim is, in other words, that there exists some subformula of the orange formula whose size is between 1/3 and 2/3 s. And to see this, it's very easy. You just so a formula, after all, is a binary tree, a rooted binary tree. So start at the top, and we're going to consider a walk down the formula, where at each point you descend to the larger of the 2 subformulas below you. And the claim is that, well, at some point we have to reach a subformula of size between 1/3 s and 2/3 s. And this is simply because each time we descend, we're reducing the size by at least 1/2, right? And therefore, it's impossible to pass from size above 2/3 s to below 1/3 s. Okay, so we find such a subformula like this. And then we do the following transformation. So consider the following formula. What I've done here is I've taken 2 copies of the yellow subformula, and then 2 copies of the red subformula, where here I'm substituting 1 for the yellow subformula, and here I'm substituting 0. And I claim that this formula on the right, it computes the same Boolean function as the formula on the left. And okay, so this is easy to see if we just sort of verbalize what is this formula doing. It's saying either the yellow subformula evaluates to 1, and this red subformula with 1 substituted evaluates to 1. Or the yellow subformula evaluates to 0, and the red subformula with 0 substituted evaluates to 1, right? So this equals 1 if and only if this guy equals 1. Okay, and then so we've transformed this. We started off with this orange formula, and we've transformed it so it has this form, and then we're going to recurse. We're just going to do the same balancing process in each of these 4 subformulas. And since each of these 4 subformulas has size at most 2/3 s, this means that this recursion only has depth order log s. And when you think about the resulting formula, this means that you note that we're increasing the depth by just 3 each time, right? So the final formula we get in this way will have depth order log s. Okay, so this is the theorem we just showed, and this leads to the following definition / corollary. So the complexity class of languages decidable by log depth circuits, so circuits of depth order log n, this is known as NC1. And as a corollary of the theorem, this class is equivalent to languages with poly-size formulas. Right, so to see why, so every log depth circuit is equivalent to a poly-size formula by part 1, and every poly-size formula is equivalent to a log depth formula by part 2, and every depth 2 formulas, and since formulas are circuits, this shows that poly-size formulas are equivalent to log depth circuits. And it moreover follows that this class NC1 is a subclass of P/poly, because poly-size formulas are a subclass of poly-size circuits. Okay, so now we have these 2 different size notions for Boolean functions. We have circuit size and formula size. And clearly, circuit size of a Boolean function is at most the minimum formula size, right? Because, I mean, the smallest formula for f is also a circuit, so that provides an upper bound on the smallest circuit size of f. So therefore, I mean, it follows that proving lower bounds for formulas is necessarily an easier task than for circuits. So we saw that proving circuit lower bounds is hard. The best lower bounds that are known are merely linear. What about formulas? So it turns out that even formula lower bounds are hard. And here's the history of the strongest known formula size lower bounds for explicit Boolean functions. So this problem has been studied for a long time, and there was a very gradual sequence of improvements, but for over 20 years, the strongest lower bounds have been stuck at just shy of cubic. So there was recently some low order improvement inside of this little o1 by Abishai et al. A few years ago, but this is one of the major frontiers in complexity theory to prove lower bounds better than n cubed. And this is also another holy grail problem in circuit complexity, to prove a super polynomial lower bound on the formula size of explicit Boolean functions. And as we saw, so this would show that NP is not contained in the class NC1. Okay, so this would be a weaker result than NP not contained in P/poly, but something which necessarily we would need to show first. And as a consequence of the theorem we just saw, this is equivalent to showing a super logarithmic lower bound on circuit depth. So a lower bound better than C log n for any constant C. So this is the last slide. Just to conclude, I wanted to mention some of the other uh, uh, complexity classes that are studied in circuit complexity in the non-uniform setting. So we've already discussed some of these. We have P/poly, which is poly-size circuits. NC1 is log depth circuits. Turns out that's contained in this class log space/poly, log width poly-size circuits. And that is contained in NC, which is polylog depth circuits. And this is sort of the non-uniform version of efficient parallel algorithms. So algorithms running in polylog time on polynomially many processors. And within NC1, so a very weak class that's often studied is known as AC0. This is constant depth circuits where we allow and OR gates to have unbounded in degree. Okay, and this is this class is sufficiently weak that there are techniques to prove strong lower bounds. In particular, it's known that the classical result in circuit complexity shows that the parity function, which is computable in NC1, is not computable in AC0. And you can read more about so yes, before giving the references, just to recap what we showed in this last part, we discussed the different resources of circuits and Turing machines, right? We saw this connection between circuit size and time complexity. We mentioned that circuit width corresponds to space complexity, and this notion of circuit depth we showed is within a constant factor of log of formula size, and this gives the definition of the class NC1. We also showed that non-uniformity is a more powerful resource than randomness. So in a non-uniform setting, every randomized algorithm can be made deterministic. And finally, we discussed the important open problem of proving superpolynomial lower bounds on formula size. This is the conjecture that NP is not contained in NC1, and the even stronger conjecture that NC1 is different from P/poly. Yes, and you can read more about circuit complexity. And Sipser's book contains a few relevant sections. There's also the Aurora Barak book, and a more advanced and more comprehensive textbook by Yukna, Complexity of Boolean Functions.